Good day, everybody, and welcome to Elmarco Talks, it's a webinar where we invite our partners in academia and industry to discuss matters related to electrospinning. Sorry, we're starting just a few minutes late. We had a slight technical difficulty, but I want to talk today about our topic. So we have a topic related to advanced bio-based and circular materials adapted for electrospinning, and we're excited to welcome Dr. Stefânia Gaspar to talk to us. She's from Arkema. First, it'll be a little different. Usually we have a panel on our side and we have one speaker. Today, Stefânia and I will share the topic. She will first present some things about Arkema, and then I will share some initial results we have from electrospinning of some of these materials that she will discuss. So first, I'm Dr. Josh Manasco. I'm Director of Application and Business Development at Elmarco. I've been with Elmarco for about 10 years, since 2014. And my background is in chemical engineering. But I want to talk also today about our special guest, Dr. Stefânia Gaspar. Her training academic background, she has a PhD in material science from INSA Lyon, and a dual degree in chemical engineering from UFU in Brazil and ENSCM in France. And Dr. Gaspar joined Arkema in 2014 as well. And she was initially in research, but now she's moved into business development manager. And so now what I'll do is I'll introduce a little bit about Elmarco, and then we'll go to Dr. Gaspar's talk. And then I'll follow with my talk after that. So just quickly about Elmarco. We are an equipment manufacturer based in Czech Republic. Here on the screen, you can see several places where we're located. We have, the industrial lines are signified by the green dots, and the orange dots are sort of our lab. So you can see there's quite a bit of machines around the world. We have a lot of machines, mostly in Europe, but we're also growing a lot into Asia and into the US, of course. And we have roughly 250 machines installed globally. Just a little bit about our technology for those that may not know. We have what's called our Nanospider technology. It is free surface-based electrospinning, where you apply the solution. You can see in the video on the side that we apply a solution to a wire. It spins, and what's nice about this method is that it's easy to maintain and keep clean, and from a standpoint of operation. But also you can see and especially in this next slide, you can see that whereas with needle-based or nozzle-based, we really dictate where the fibers are being spun from. But with our technology, physics dictates where the jet placement is on the spinning process, and we really believe this gives you a nice homogeneous electrospinning. You can see that the jets look like they're going up, down, inside into the screen, but all of them are being attracted and being collected on a substrate that is above the spinning electrode. We have, as I mentioned, we are an equipment manufacturer. We have equipment based on the lab scale, which is our NS lab, the one on the top left. We also have another line that we can call our small production, which is NS3S. And then we have industrial scale lines, which NS4S, NS8S, and the Infinity line. So we can do the work for you from the lab scale all the way through the industrial scale in the electrospinning process. One thing I want to highlight is that you may have noticed, if you're familiar with Elmarco, that we used to call this the NS1S, but now it's the NS3S. We have added 2 more electrodes to the machine so that we can increase the flexibility and the throughput of the equipment. We also have a couple of additional collecting electrodes, a rotating electrode, which you can make some very unique 3D type structures or some pieces, and we also and maybe even do some aligned fibers. And then we also have an endless belt that works well with substrates that are more resistive or sometimes more difficult to spin onto. A lot of you here probably know, but we have, there's a wide range of nanofiber applications, from air filtration to liquid filtration. Of course, the hot topic now also is energy and performance apparel. These are all typical applications that electrospinning and nanofiber serve well into. And I'm sure that we'll talk about some of those today with Dr. Gaspar and with my further discussion on the electrospinning and your questions, of course. I do want to say that if you have questions, please put the questions in the Q&A part of the screen, and we'll get to those once we get through both Dr. Gaspar and then also my talk.
So thanks again for the kind introduction and for the opportunity for being here today. So I'm in charge for the business and development activities for Arkema, and I'm in charge for the industry and textile markets. So today you present some insights about our company, our main activities, and we will focus on our advanced bio-based and circular materials adapted for electrospinning, and we are very glad that Elmarco could evaluate and test our products in their technology. So first I will share a brief introduction about our company, explain about our unique bio-based value chain, introduce the main properties of our Rilsan polyamide 11, which is 100% bio-based long-chain polyamide. Also, I will introduce some key properties about our TPE under the brand Pebax and Pebax Rnew for the bio-based grades, and explain why it's a circular solution. So first of all, Arkema is a French company. We are present globally, and definitely our vision is to be a leader on specialty materials, specialty solutions, offering the most innovative and sustainable solutions for our customers for the current and future challenges. So our activities are based in three main pillars. So the first one is adhesive solutions. The second one is coating solutions. And the third one, advanced materials. So I'm part of these advanced materials, which represents more than 30% of our annual sales. So in 2023, our results lead to 9.5 billion on sales. As I said, we are a French company, but we are present globally in more than 50 countries. We have more than 150 production facilities with more than 21,000 employees, and we invest a lot on research. So we have 17 R&D centers. We fulfill yearly hundreds of patents, and definitely as R&D is key for us, and we invest a lot on innovation. So now let's focus more on our portfolio. So inside advanced materials, we have our business unit, high performance polymers, and here you have the main products. So as you can see here in this classification, so we are really focused on the high performance and ultra performance materials. So starting from the top, we have our PEG, so under the brand Capstone, which is mainly used in aeronautics, composites application, defense, military applications for very demanding and outstanding applications. We have, of course, the PVDF under the brand Kynar. Orgasol, which is a very specific powder used in some specific composites applications for aeronautics, but also in cosmetics due to the very good soft hand feeling used in cosmetic powders. And today we will focus more on our polyamide 11, so Rilsan, and on our Pebax that I will give more details later. So considering these two products, they are really important for us, and we just invested on these new product lines. So for polyamide 11, we just increased our capacity per 50% with a new plant that started in Singapore last year. And also we increased our capacity for Pebax per 40% with a new line here in Cerquigny in France. Now, let's talk more about our bio-based and unique value chain. So when you talk about bio-based materials, it's important to highlight that this is definitely not new for Arkema, because since 1947, Arkema has producing our polyamide 11. Okay, so then the brand Rilsan comes from the river that we have here in Normandy called La Rile. And since the very beginning, it was from our from castor oil. So we will explain later about our raw material, but I would like just to reinforce that since more than 75 years, we are producing polyamide 11, a bio-based product. Everything started, as you can see here, during the Second War. And the motivation that time was really to be independent from fossil-based energies. And for the French engineers and researchers at that time, they were really proud to have their French nylon with very good properties that we will see later. So everything starts from the castor plant. Okay, so this plant grows mainly in semi-arid soils, in marginal soils, in a region called Gujarat in India. Okay, so today, 8% of the global production comes from this region. This is a very specific plant because as it grows in marginal soils, there is no competition with food or feed. There is no deforestation. It uses very limited water and takes profit of a natural phenomenon in India, which is the natural monsoon. And with one plant, we can have 5 pickings along the year. So from the plant, we extract the beans. These beans are definitely very profitable for the Indian farmers. So they really use it as a cash crop for them. So they can store it and they can decide to sell it in the trader markets, depending to the price, if they need money at this moment or not. So from the castor bean, we crush. We obtain the castor oil, 45%, and 55% is the cake. This cake is also valorized under a very important biofertilizer, and the oil is the basis of our chemistry. So Arkema buys the castor oil, and here we will split, so it's a molecule with 18 carbons, and we will have the chemistry of our C7, also valorized under our product range oleries, so some lubricants, flavors, fragrances. So it's really important to valorize all the value chain. And the chemistry for our C11 will give birth, I would say, to our monomer, which is an amino carboxylic acid. So we need only one monomer. And then we polymerize and we obtain the polyamide 11. So Arkema is fully integrated from the monomer to the polymer. And another, just to share, so here we are talking about 700,000 farmers in India. We are talking about family farms. So it's completely a different ecosystem from what we can see from soya or palm oil, for example. I do not have much time to disclose here, but I would like just to share that Arkema is also part of an initiative called Pragati, which is definitely very interesting to support the daily work from the farmers in India. So as we produce the monomer, so then we can play with the chemistry. We are a polymer producer. So either we can have our polyamide 11, as I said, Rilsan, and then we can play with the monomer, associate with other monomers, the other functionalities, and we can have a very broad product portfolio from some PPA, some Rilsan high temperature, some amorphous and transparent polyamide, some powders, and TP. So I cannot disclose everything, but just to share that you have a very broad product portfolio, bio-based, with very specific properties adapted to many different markets. So thanks to our portfolio, we can cover applications from oil and gas, passing through automotive applications, consumer goods, textile, sports. So it's definitely very broad. We have solutions adapted for different processing technologies, so injection molding, extrusion, 3D printing, and so on. And we are also very happy that we can also test our products in electrospinning. Now, just let's talk more about polyamide 11 and its main properties. Okay, so polyamide 11 is a long-chain polyamide. As we said, it's definitely very, very light. So as you can see here, in terms of density, it's about 1. So lower, yes, of course, compared to short-chain polyamides and the other materials that you can find, like PVDF, for example. As it's a long-chain polyamide, you have a very low moisture uptake. If we compare, for example, with polyester, we are in the same range of polyester. I should add here, but yes, polyamide 11 is also close to polyester, so very low moisture uptake. In terms of melting point, we are about 190 degrees. So this low processing temperature is also very good to save energy, also in some processing, in some technologies, and save energy. Here I'd like just to reinforce about some difference that we can find when you compare polyamide 11 and polyamide 12. Maybe you can think that these polymers are very similar, but not. The difference linked to just 1 carbon less with polyamide 11 leads to a very unique properties on this polymer. So this is due to the crystalline structure. So we have alpha triclinic with polyamide 11, meaning that all the amide functions are completely aligned independently to the orientation of the polymer chain, which is different from polyamide 12, which is gamma clinic. As a result, we have a more compact and a more thinner morphology when you look here into the spherulites of polyamide 11 compared to polyamide 12. And as a result, you see a difference on impact resistance, especially at temperatures in which polyamide 11 is 2 times higher, more resistant than polyamide 12. But also here, I thought that maybe it could be interesting for some of your applications. So due to this more regular and thinner morphology, when you look on gas selectivity and permeability, and you compare to PA11 and a PA12 with similar molecular weight, and then you look into permeability to gas, you see that, yes, with polyamide 11, we can have a better selectivity, lower permeation compared to polyamide 12. To finalize on some key properties of polyamide 11, I'd like to highlight about the chemical resistance. Here again, as it's a long-chain polyamide, the interest of this product compared to polyamide 6 or 6,6 is definitely the use for applications in which we can have, we are in contact with a lot of chemicals, harsh chemicals, and for which we need long durability. So here you have some results when which we have these different tubes, and we passed some ZNCl2, drove the tubes, and then we look the behavior over time. So with polyamide 6, we have an instantaneous crack. With 610 and 612, with slightly higher long chain, we have longer GSC here. We have cracking, but it's a bit delayed. But on long term, as you can see here, a lot of swelling, we may have some leakage. And on the other hand, with even longer chain polyamides, you have no cracking, no change on properties. So I presented in some slides previously some key markets in which we are present. We saw offshore applications and automotive. And the main reason is definitely the durability due to the chemical and hydrolysis resistance. Last but not least, of course, when you talk about bio-based polymers, it's important to mention about the carbon footprint and where we are polyamide 11 today. So when you compare polyamide 11 to other fossil-based polymers, so today we improved these numbers per 70%. So we are 70% below compared to fossil-based polyamides in average. So this is due to the biogenic carbon, because it's a bio-based polymer, as we said, and the use of biomethane energy. So this is due to all the decarbonization actions that are put in place by Arkema. So this number today is public. So if you look in our press release, you can find the number. So K11 carbon footprint is below than 2. So this is public today, and this applies to our entire global production. It's not limited to specific grades or specific plants. It's really a corporate decision and actions ongoing on decarbonization, and we have a very clear target also for 2030, in which the goal is to decrease per 50% this number. Now, very shortly about Pebax. So what is Pebax? So it's a thermoplastic elastomer, okay? It's made by 2 blocks. So we have a rigid block made on polyamide. So this rigid block can be either polyamide 12, polyamide 6, and of course, polyamide 11. So when it's based on polyamide 11, it's our Pebax Rnew product range. So the polyamide block, you provide chemical resistance, good mechanical properties to our Pebax. And we have a soft block, which is a polyether. Okay, so this polyether with a very low glass transition temperature leads Pebax to the material of choice for winter applications, for example, for markets in which we need to ensure a very good mechanical stability over a very broad range of temperature. We can have some elasticity due to this soft block as well. And we can play with the nature of the polyether that can be either hydrophobic or hydrophilic. When you have hydrophilic polyether in our composition, our Pebax can be used as permanent antistatic additives, or as well as breathable solutions, for example, for breathable membranes, for apparels, for example, or for house wrap membranes. So we can have also these breathable grades. Yes, and then what Arkema can do is we will play, okay, with the nature of these 2 blocks, the polyamide and the polyether. We can play with the content. And at the end, we can have a very broad product portfolio from very soft Pebax with very low flex from modulus, less than 20 MPa, up to almost more than 800 MPa. So the rigid, the Pebax, of course, the highest the content of polyamide. So here I'm presenting only the bio-based range, or only the Pebax Rnew range. And here you have an indication on the bio-based content, which comes, as you understood, from the polyamide 11 block. And you have the equivalent on polyamide 12 as well. In terms of properties, so Pebax is definitely very light as well. So when you compare to TPU, other TPE, here you can see the gap. So in average, Pebax has a density about 1. And as I said, due to this very low glass transition temperature coming from the polyether, we can ensure a very good stability in very different environments. So for example, if you look the modulus at 23 degrees and -13 on Pebax compared to other TPUs, you see that the gap is lower. With TPU, we can have this rigidification at a very lower temperature, so leading to breakage, to a bad durability with TPU. And at the end, yes, we are present in many, many different applications. Pebax today is a brand for us. It's well known in the sport applications, mainly for the running shoes, Pebax foam, for example, in the ski boots. But also we are well present in industrial applications for some catheters here, in which we can have several Pebax grades in the same catheter. Yes, for breathable membranes, as I said, with our hydrophilic Pebax, in industrial applications and so on. So it's definitely very broad. And to finalize, both Pebax and polyamide 11 can be mechanically recyclable. Okay, and today Arkema is completely integrated with our bio-based offer and recycled solutions, thanks to the acquisition of an Italian company called Agiplast in 2021. And today we can provide this Virtucycle program to our partners and customers. What does it mean? It means that we can collect post-industrial scraps from your productions, for example, and then we can buy it, and we will use these scraps. We will formulate with other virgin materials, for example, and we will develop or another engineering plastic. Okay, for it's really upcycling, it's not downcycling, for another end use, and the content of recycled content can be from 30 up to 100%. And also, so this is talk about open loop. But if you have any project for which you'd like to work on eco-design, monomaterial solution, thanks to our portfolio, we can definitely provide them the best choice, and follow our partners and their projects if they'd like to have, since the beginning of the project, a solution for recycling. So that's all from my side. I hope that you could have a brief understanding about these two main products. And now I leave the floor to Mr. Manasco to present the very good results with our products. Thank you very much.
Yeah, thank you, Stefânia. So I will share my screen, and I will talk a little bit about some of the results we have from spinning. And a lot of our results will be based on, hold on one second, So we'll talk about electrospinning. So we very gracious to Dr. Gaspar and Arkema for working with us and sending us lots of samples to work with. And we have some very interesting results, primarily from Pebax. I'll talk a little bit about Rilsan as well. But we had a search that we were going for, and we were looking to do some development of air filtration materials. And there's a need in the market for some durable materials for air filtration so that you can reach higher efficiencies. So we were looking at HEPA filtration, higher efficiencies on the scale, and also the need for the material to be IPA resistant. So right now we consider, and a lot of our businesses in air filtration, we consider PA6 or nylon 6 as our, let's say, gold standard for comparing to other new materials that we want to look at for air filtration application. And so what we want to do is we want to maintain the throughput that we get from PA6, because we know electrospinning, we have to keep the throughput up, and we want to make sure that we're producing a lot of nanofibers over time. But we also want to use non-toxic solvents if possible. And then when we talk about figure of merit, we want to make sure that we maintain the pressure drop to performance ratio that we get. We see PA6 as a very good model for this to look at and compare. It does quite well for most air filtration applications. So again, we're looking for a more durable layer for downstream processing, meaning lamination, pleating, and filter making. So we were in discussion with Arkema about potential materials. We started looking at Pebax as a TPE. We were looking at some TPUs, but they had some drawbacks of not being IPA resistant, or some of the solvents weren't so nice. But we found this really nice material in Pebax that you can control the softness and hydrophobicity, as Stefânia was discussing. And we received 3 grades initially from Arkema, this 2533 up to 4533, and that's just increasing in hardness through those 3 grades. And the good thing about these 3 grades is that we found that they're soluble in formic and acetic acid, which we consider to be more bio-friendly or green solvents, let's say, compared to DMAC, DMF, and those types of solvents. So the initial results, we looked at the first softest grade 2533, spun very well, and both the 2533 and the 3533 electrospun quite well. For this application, we weren't looking for this much elasticity and tackiness, but for other applications, it could serve well for that. And I apologize, I can't share every result from everything we've been doing with the Pebax, because a lot of them are related with our different customers and partners. But in this case, for this application, looking at air filtration, we wanted to look at slightly harder grade, which was the Pebax 4533. And you can see before, where whenever you peeled the membrane off, it became quite tacky and sticky together, which again, I said, could work well for certain applications. But in our application, we want to have a membrane that doesn't shrink so much and have so much tackiness for this particular air filtration application. So the 4533, all of them spun quite well. The 4533 also spun quite well in our process, and we were able to make a nice membranes from them. The other nice thing about the Pebax is that you can get good spinning from quite a wide range of concentration. So we looked at concentrations of Pebax down from 6% all the way to 12%. We can probably go lower and higher even. We haven't studied everything fully yet, but you can see that there's a nice fiber formation from these materials. And then also the mean fiber diameter range that we've achieved quite easily between just looking at the concentration in a mixture of formic and acetic acid. You can see that this is quite interesting and quite useful to be able to achieve these types of fiber diameters when you're looking at tuning different properties. I'd like to say also that you can use, I don't have all the results here, but relative humidity, similar to what you can do with other polymers, you can sort of modify the mean fiber diameter by changing the relative humidity, and also along with the concentration, and then also the ratio of acids in your solution. So it's a quite versatile material and quite easy to spin. If we want to look at some initial filtration results, and we compare it again to nylon 6, you can see that, and if you want to start looking first at the results between before and after discharging, what we do to discharge an IPA, it's related to ISO standards that you want to be able to make sure that once the material is exposed into humidity or anything like that, that the material doesn't discharge and lose its efficiency. So we use IPA, and we simply put these in an IPA vapor for 24 hours. And you can see the PA6, it loses a little bit of filtration efficiency from IPA, but it still maintains quite a bit. You can see the Pebax does even better in terms of IPA resistance. We don't really lose the efficiency after discharging. This is quite important for us in air filtration applications. Also to note, the line speeds we were running here, you can see that the highlighted one's in red. The pressure drop, which is sort of, we can relate back to the throughput, the pressure drop add-on for both of these polymers was very similar. So we're seeing that we have the throughput is quite similar between nylon and Pebax. So we're not losing anything there. And then you can see that we were able to achieve HEPA, like H13 all the way up to U15 in the flat sheet materials that we're showing here. And that's quite important to us. The important thing is that this material is a lot more flexible and durable than PA6, which is very crystalline and can be a little bit fragile and is subject to cracking and things like that when you start to do downstream processing. And then we also have looked at Rilsan. We've been so excited about the Pebax results that we haven't been able to spend quite as much time with Rilsan, but we have looked at quite a few solvent systems to try to spin this. The one challenge that we've come across is it's not, of course, it's not soluble in the acetic and formic acid, but we have found a couple of different solvent combinations that do work. Formic mixed with dichloromethane, and then also phenol mixed with formic acid, and we've been able to achieve fibers from Rilsan. This is still in the works. We're going to continue to pursue this work with Rilsan to try to see if we can make nice smooth fibers and demonstrate this similar flexibility that we see with the Pebax and nylon 6 is our goal. So just briefly, the conclusions. Pebax is, from what we can see, is very promising to make durable nanofiber webs. The initial results that I've shared here, it shows that it's very similar to nylon 6 in terms of throughput and the figure of merit, meaning the amount of performance you get from the pressure drop that you add on. It's IPA resistant. And we're currently testing the materials that we're making from Pebax in lamination and pleating process and filter making with several of our partners. So this is a very exciting time for us. And we're going to compare that to what we see from nylon 6. And then we're also, Arkema is very kind to send us even more different grades of the Pebax, including the Renew. So we're working with those as well. Don't have those results here today, but they will be soon. We'll soon have some of those results. And as I mentioned with Rilsan, we're continuing to look for and also a sort of a green solvent for Rilsan that works well for the spinning process. And we're making some headway there, but not anything to present today. So with that, that's my results that I wanted to share today with the audience. And let me stop sharing, and we will take questions from the audience. And the way we'll work is I'll if it looks like it's for me or for Stefânia, we'll try to, or we can tag team them. So Stefânia, we had a question from the audience about molecular weight. Do you have any molecular weight charts or any sort of indication on molecular weight for some of the different materials you were discussing?
Yes, so we have a very large portfolio. For the most, I would say, fluid grades, we're talking about 10,000 but we have very viscous grade because we are present in extrusion pipes applications, so more than 60,000. So it's really very broad. I would say we can definitely found a solution depending to your requirements for both Pebax and P11. Pebax grades are mainly focused for injection molding applications, so we are really on the low, medium molecular weight.
Thank you. We also have a question about the difference in elastic modulus between PA11 and PA12. Do you have any comments about that?
Yes, it should be very similar. It's between 1,200 MPa. So yeah, they are very similar. It's both. It's in terms of mechanical properties here on modulus, they are similar. The main difference between both will be on creep resistance, impact resistance, mainly at low temperatures, as you said, and on elastic behavior. But then, yes, I can, if you would like to send me an email, I can send you a chart just to explain the difference on creep resistance and elasticity between polyamide 11 and polyamide 12, which is linked to the crystalline, as I explained it in the beginning.
Leading out from that question, or your answer at least, there's a question for me on the amorphous or crystalline nature of a polymer affect nanofiber formation. It certainly can. I mean, of course, the more crystalline some polymers are, the harder they are to dissolve in solvents. But really what we see is that some of the more amorphous materials, you can see that the fibers that you make may look more like a bowl of spaghetti or like a membrane. And the more crystalline nature polymers might be more stretched out, and a more thin, more like stretched fiber may look more like sticks laying on top of each other. And that can affect, of course, cohesion of the materials to each other. The one thing about Pebax that's nice is that we get a good cohesion of the material together. The material sort of, let's say, solvent welds together, and it forms more of a membrane type structure, whereas something like nylon 6 looks more like those sticks stacked on top of each other, and it's a little more rigid material, and we don't quite get as much of the cohesion between the fibers together, which what we see is that cohesion and the more membrane-like structure can give you a more durable material whenever we're looking at the final properties. So it does affect the spinning, but it also, I think, mainly affects the membrane properties or the web properties of the material. One more question for me about figure of merit performance. Didn't get into too much detail about this. A lot of companies use different ones, alpha or gamma. It's basically a ratio of pressure drop to filtration efficiency or penetration. So the higher the figure of merit usually means, or always means, that you have a better performing material. If you have two materials with the same filtration efficiency, but one has double the pressure drop, then your figure of merit will be much lower for that material that has a higher pressure drop. So that's the basic. It's defined in a lot of different ways. But if you have a question afterwards and you want to email me about more, then I can answer in more detail about that. How thermally stable are nanofiber architectures of Pebax samples? So I think one thing that I guess you can discuss, Stefânia, is about melting point of these Pebax grades, because of course, the closer it is to nylon, it's going to have a higher melting point, and then the softer materials will have a lower melting. Do you mind to make some comments about the melting points?
Yes. Yes, so on Pebax, we start from about 130, and we can go up to 175. So as you could see, the product range is very broad, depending on the softness. But yeah, basically between 130 and 175 in Pebax.
And in general, about thermal stability in nanofiber membranes, what we do see a lot of times is that in the bulk properties, you'll see a little bit higher melting point than in nanofiber form. And when you're in the nanofiber form, typically you do see a little bit lower melting point. So I would say that you just have to take that into account. Let's see. One question here: is it possible to form yarn from PA11?
Yes. We have a specific grade. If I talk about multi-filaments, so we have a specific grade, and we have a partner that can do PA11 multi-filaments in Europe. So if you are interested, you can also get in contact with me. I can share the coordinates, but also monofilaments is possible, and the staple fibers. So you have all the value chain on the yarn for PA11.
And there's a question about the Virtucycle, Stefânia. Do you consider a study on possibly recycled non-woven webs?
Yes. So today what we recycle is polyamide 11 Pebax PA12 products, different scraps. As I said, today we are already recycling textile scraps, so PA11 monofilaments, multifilaments, some knitting samples. So we can definitely also work on non-woven webs. The point is to see if you are talking about post-production scraps or post-consumer, if there is some contamination or not. But in any case, we always discuss on their case-per-case basis to provide a reply in terms of feasibility.
And then let's see. It's maybe about the medical grades. Are the materials that you discussed, are they medical grade, or are there medical grade options?
Yes, so on the Pebax, the 33 series, so not the bio-based one, they are medical approved. We have also food contact, FDA, the same for some specific PA11 grades. So yes.
I would say one of the things that brought me back to Pebax was my time at Zeus Industrial Products before we were making medical devices using Pebax. So it's definitely in being used already for many years there.
Exactly. Yeah.
And let's see, what about issues concerning long-term availability of castor seeds for your business model? Are you ever considering replacing castor oil as a feed for PA11?
Yeah, so as I said, we are producing polyamide 11 since more than 75 years from castor oil. What's important to note is that polymer business is not the first market for castor oil, because we can use it in cosmetics, in pharmaceuticals as well. So castor oil for polymers, and not only polyamide 11, of course, because you can have other chemicals derivative from castor oil. It's only 20% of the global production. So definitely, no, there is no risk, I would like to say. And also, as Arkema, we have an internal project today that we will start to communicate, I think, along this year, in which we are already work with other regions in the globe to avoid any, for example, geopolitical issue in the future. So, of course, today we are supplying mainly from India, but today we have already 2 other sources in the globe, always considering the same criteria in terms of competition of food or feed, the quality of soil. So, but we are also looking on it, and no, there is no risk on shortage, because it's really one small part of the global market for castor oil.
Thank you for that. I have one question from myself related to that. What about mainly about the growth of the materials? I know that you guys have been building up your production. What applications do you see the biggest growth in for Rilsan or Pebax?
Okay, so today on PA11 we have a lot of work ongoing for hydrogen tanks, so hydrogen. So with polyamide 11, because it can be used in many different technologies. If you on the hydrogen segment, 3D printing today for both polyamide 11 and Pebax. Textile for us is also a growth market for PA11, so we also trust a lot on it. Yes, and yeah, sports as well, yes. But I would say today for us, our main priority is the hydrogen applications.
And for Pebax?
And for Pebax, 3D printing. Let's say 3D printing, sports, yes.
I think it's a question for me. Generally speaking, is it difficult to find nanofibers that are resistant to IPA? I was mentioning during the talk that we were looking at something like a TPU, for instance, to give us some more durability, that elastic membrane type effect that could potentially go through lamination or pleating better. It is difficult because a lot of the polyurethanes, it's hard to find the polyurethane that spins very well, but also is IPA resistant. That's been our experience. So and also then looking at the solvents. So to find a polymer that has this elasticity, is IPA resistant, and is spun from these solvents that I would consider to be more benign. Pebax is that triangle of things. Pebax is quite impressive to achieve those things. So it's hard to find not hard to find a polymer that might be resistant to IPA, but it's hard to find a polymer that's resistant to IPA that has those other attributes that we're looking for. That's what I would say. So let's see. Have you tried using natural polymers such as cellulose? If so, yeah, you can electrospin like lignins, electrospin cellulose acetate, those types of materials. A lot of people are looking at those, electrospinning those things to then carbonize and make into carbon materials, carbon fiber, carbon powders, different things like that as an alternative for carbon. But yeah, you can spin those. If you have more interest, please just send a note, and we can definitely connect and discuss more. What is the range of pore sizes you can make with your machine? Typically down to 0.1 micron is, maybe a little lower than that is probably the range, and then you can go up to half a micron, 1 micron. You can maybe even make bigger. That's usually not the problem that we're trying to solve. We're usually trying to go smaller, but 100 nanometers, 0.1 micron is something that's relatively achievable for most electrospun materials. What techniques do you use for electrospinning, and what is the size of your sheet, surface area, dimensions? So our machines are typically roll to roll, except for the 3D, let's say, spinning electrode I mentioned from the NS3S. We're typically doing roll to roll electrospinning, which means we're making rolls of material, not just a sheet. I was showing a sheet here in the presentation from the Pebax because that was just a sample we had cut from a roll, just to illustrate the, let's say, the shrinkage or the tackiness of the material. But typically we're making roll to roll. Our biggest line is 1.6, our standard industrial line is 1.6 meters wide. And then, you can put a quite long hundreds or thousands of meters of roll on that to make, make a material that's quite a long roll. So, okay. One more thing is, Stefânia, you mentioned the Pragati program. Can you say a little bit more about that?
Yeah, so Pragat is an initiative started in 2016. So Arkema, BASF, NGO, and a company producing derivatives from castor oil in India. So we are the four founder members. And here idea is to train the farmers in India to help them to apply good agricultural practices, ensure that they can improve their yield. Because as I said, we are talking about family farms, so helping them to improve productivity with the same portion of land. And then they can be certified, audited, and it's a program that is starting 2016, and year per year we are training more and more farmers. But today we are at about 7,000 farmers trained and certified, and the idea is to increase even more this program with some digital tools and support from our partners.
Very nice. Thank you for sharing about that. We had a question about sharing emails. So Stefânia's email was in her last slide in the deck. I think we'll also be able to connect everybody through LinkedIn. And if you want to follow up, I think there's many ways to follow up from this webinar. And that reminds me, please follow us on LinkedIn, and we will have more webinars in the future, just a reminder. And I think we're wrapping up here, but there's a couple more questions, I think specifically for me, Stefânia, about electrospinning. How is the productivity compared with PA6? Can you obtain the same quantity of nanofibers per hour? So when we're talking about quantity of nanofibers or throughput, all the fibers aren't exactly the same size, of course. So we're looking at building blocks. We normally look at grams per square meter or added pressure drop to indicate what we're doing in terms of throughput. You can also use thickness, but it's quite difficult to measure thickness of soft materials, as a lot of people know. But what I would say is about Pebax versus PA6, for the same line speeds, we were seeing very similar pressure drop add-on, which means that we're adding a very similar barrier to airflow in that situation. It's not always 100% apples to apples, but that's a good indication to us. And then you look at efficiency, and you can see that you're achieving efficiency either on the same level or even better. And so you go back and you look more at less about how many nanofibers you're producing and more about what the performance is of those nanofibers in practice. So air permeability, pressure drop, filtration efficiency, using those types of things as the measure. So it looks like we're just out of time now. And Stefânia, I would like to thank you very much for joining us and providing your expertise. Like we mentioned, we can follow up. Stefânia's email address is on her contact information is there. Please follow up with her on any questions about the polymers. Follow up with us on any questions about electrospinning. And Stefânia and I will help each other to sort out your questions and sort out how to serve you guys in your questions. So I'd like to thank everybody for joining us today. And like I said, look out for the next series of next webinar series on LinkedIn. So thank you once again, Dr. Gaspar.
Thank you very much. Thank you, everyone.